In this video, we're going to look at some background information that will help you understand a future video on the process of nuclear fusion going on in our sun. And this process of nuclear fusion happens in nearly all stars. The most massive stars have a somewhat different process going on in them, but for most stars, for most of their lives, this is the process going on in the center. This process we're going to be learning about takes place because of three forces that are acting inside a star. There's actually a fourth force that plays a role as well, but we'll limit ourselves to these three. First is the gravitational force that acts between all objects that have mass, including the protons, neutrons, and electrons that make up the star. The net result of this force is that all the parts of the star feel an attraction toward the center of the star. The next force is the electric attraction and repulsion between the particles that make up the star, particularly the repulsion the protons feel toward each other. Finally, there's the strong nuclear force. This will hold nuclei together, but before it can act, the particles have to get very close together. So let's look at each of these forces in a little more detail. Gravity is the force that starts the whole process that we're interested in. It's gravity that causes the collapse of enormous clouds of gas and dust in space, pulling all those particles in the direction of their common center of mass. Once they have formed the star, more or less, the net gravitational force pulls toward the center of that star, and we need to start thinking about how the bottom layers have to support the weight of all the material above, just like the bottom person on a stack of acrobats standing on each other's shoulders has to hold everyone else up. If the material that forms a planet has enough mass, the planet will be squashed into a spherical shape by its own self-gravity. In the case of a star, if the star has enough mass, it will cause nuclear fusion to start up in the center of the star. That's actually what determines whether or not something is a star. For the electromagnetic force, we need to think about something, just the electric part of it, which we call Coulomb's law. And Coulomb's law starts off with the idea that opposite charges attract, and those opposite charges would be positive in one case and negative in the other, and like charges will repel each other. Like charges, either positive and positive or negative and negative, repulse each other. This is the origin of the phrase opposites attract, by the way. In the sun, the things we're concerned about are all charged particles. Positively charged protons, which we'll be calling hydrogen nuclei, helium nuclei, which is a bundle of two protons and two neutrons held together by the strong force, and negatively charged electrons. A final feature of Coulomb's law is that the electric force between charged particles gets weaker with the square of the distance as that distance increases, but as they get closer together, that repulsive force gets much stronger. The closer the two nuclei are to each other, the greater the repulsion between them. And then electrons in this case are moving too fast to stick to the nuclei. It's just too hot in the sun for that to happen. So the electrons are running around free. Finally, we get to the strong nuclear force. This is by far the strongest force in nature, but it's short range, and it doesn't do anything at all until the particles it acts on, protons and neutrons in our case, get within 10 to the minus 15th meters of each other. That's a millionth of a billionth of a meter, or a millionth of a nanometer, if you want to think of it that way. There's an entire class of particles that are immune to the strong force. Electrons are in that class of particles, and so is another particle we'll learn about that plays a role here, called a neutrino. And a neutrino is not a neutron. It's a different type of particle, but electrons and neutrinos are immune to the strong force. So even though it's the strongest force in nature, it doesn't even act on those particles. Okay, we're going to learn a little bit of information about some terminology we'll use, some of which you may already know, and I've been using some of it. The first one is nuclei. I've been using that quite a bit. That just refers to more than one nucleus. Another one is the term nucleon. Just as men and women can both be referred to as people or persons, protons and neutrons can be referred to as nucleons. The sum of the numbers of neutrons and protons in a nucleus is called the nucleon number, and it's also called the mass number or the isotope number. You may hear those terms used at times. Nuclei of a particular element always have the same number of protons. Okay, that proton number is sometimes called the atomic number or just the element number, but they can come in versions with differing number of neutrons. And the different versions of nuclei for an element are called its isotopes. Potassium, for instance, has 21 different isotopes. They all have the same number of protons, but they have varying numbers of neutrons. Most of them are not stable, by the way. They're radioactive and decay fairly quickly. But there are a few stable isotopes for potassium. Let's learn a little bit about some other physics shorthand notation. This is a way that we can quickly write down for a particular nucleus how many neutrons and protons and nucleons it has. And we're going to consider the isotope of gold that has 195 nucleons. We call that gold 195, and that's a way that we could state it out loud. Now, if it's gold, all the isotopes of gold have 79 protons. If it doesn't have 79 protons, it isn't gold, it's something else. So we always know it's going to have 79 protons. The proton number plus the neutron number for this isotope will equal 195. So the neutron number is just 195 minus 79. Take the total number minus the proton number, and what's left is the neutron number. Here's a different way of writing that notation for the isotope. Au is the chemical symbol for gold. It doesn't mean astronomical units here. It's just short for the term, the word aurum, which is the Latin name for gold. It means shine. Sometimes you'll hear it said that it means shining dawn, but that's actually combining two different words for gold from two different languages. We put the isotope number above the chemical symbol and to the left of it. It's like a superscript on the left side. We can do a little bit more with this notation, and we need to, because most of us don't have elements memorized by their atomic numbers. And so we'll see the symbol for something, and unless you're taking chemistry and you're fresh on it, you won't know what the atomic number is or what the number of protons is. So you may need help. So here's what we can do with this. We always start with the chemical symbol. Then the isotope number goes as a superscript on the left side. Since it's gold, we know it's going to have 79 protons. And over on the right side, we'll put the neutron number. Now, those two numbers on the bottom added together will add up to the isotope number or the nucleon number. The number of protons, 79, plus the number of neutrons, 116, equals the 195. We're not going to have to deal with things all that complicated because we're only going to be considering two isotopes of hydrogen and two isotopes of helium. And so let's have a look at those. The first one is hydrogen 1. This is the isotope of hydrogen that has a single nucleon. But since it's hydrogen, we know what that nucleon is. Hydrogen always has one proton. And so down here is the proton number. There is no neutron, and so over on the right side at the bottom, we put a 0 because there are no neutrons in this isotope. This is so simple that we're just going to refer to this as hydrogen 1. In fact, we're going to use this notation for all four of these isotopes, but we'll go through them here so in the future you'll know what they are. The next one we'll consider is hydrogen 2. This is another isotope of hydrogen. It exists here on Earth. It's a natural, stable isotope of hydrogen. Since it's hydrogen, it has one proton, but in this case with two nucleons, And one of those being a proton, the other one must be a neutron. So this isotope of hydrogen in its nucleus has one proton and one neutron, but it's simple enough that we're just going to call it hydrogen 2 and let it go at that. Now our isotopes of helium that we'll consider here, the first one is helium 3. Helium is atomic number 2. It always has 2 protons in the nucleus. Since it has 3 nucleons and 2 of them are protons, the other one must be a neutron. So there's that. And notice the proton number 2 plus the neutron number 1 is equal to the 3 there. But we're just going to refer to this as helium 3. And try to remember that helium always has 2 protons. And then our final isotope that we have to worry about in this unit is helium 4. Now you can probably figure out what it's got in its nucleus. 2 of the nucleons are going to be protons. If it wasn't 2 protons, it wouldn't be helium. And the other 2 are going to be neutrons. So 2 plus 2 is 4. Try to follow that one. And that's the proton number plus the neutron number equals the nucleon number. And those are the 4 isotopes that we need to worry about. And they're pretty much the only isotopes we're going to worry about in this class. So there we have it. And we'll just write that as helium 4.